Good afternoon or morning or in the middle. So Kelsi Singer is talking today about the exploration of distant worlds in the Kuiper belt. She is actually currently working on the Southwest Research Institute. She is a planetary scientist, expert on impact cratering, geologic mapping, spacecraft observation planning, data analysis, astrobiology, and a longer list, but I'm stopping here. She's currently focused on the study of the geology and geophysics of Pluto, Charon, and MU69 as a deputy project scientist, and co-I on NASA's New Horizons spacecraft mission to the Kuiper belt. And she was recently awarded the 2019 Harold C. Urey Prize by the American Astronomical Society's Division for Planetary Science. So we are very glad that you are here talking for us. I think she wanted to know a little bit more about us. So
Thank you
before starting.
Yeah, I knew it would be probably a little mix of people's expertise in the audience today. So first of all, I'm interested to know what you want to know more about, because I could talk about New Horizons results for like 3 days straight and still have plenty to say. So keep that in mind, and please just ask me what you want to know more about. And I just thought maybe if you'd say like quickly your name and what your area of expertise is. I know some of you, but not all of you in the room. So I know Estella, I know Dan, but I don't know you, so.
Kevin Cannon, I'm Dan's postdoc.
Okay.
I do remote sensing and space resources.
Okay, great. I know you too, but you can say your area of expertise if you want.
Yes, the regolith technology that interacts with regolith.
Great.
And my name is Ana Carolina. I work for NOAA, and now I'm working with Lucy targets.
Ah, great.
Ground-based observations to help the mission.
Okay. Is your area of expertise in like spectroscopy or?
Spectroscopy,
Okay.
photometry, piano, scaling.
Great. Thanks. I've seen your name, but nice to meet you.
So I'm with the Florida Space Grant Consortium. It's a NASA program. But my background in my previous life was towards binary stars and exchange of masses between the stars.
Interesting. Slightly different mass size scale range, but than what we're going to talk about today. But we have binaries too. Thank you very much.
I'm Mario. I'm a Noebi's postdoc too. I work with different primitive asteroid spectroscopy survey.
Okay.
Mostly asteroid family.
Cool. I apologize, I didn't include a lot of squiggly lines in this presentation, but I do have some bit of composition information. And I know you as well.
Yes. I just wanted to mention that related with what you do at this moment, with Carol, we're working on rotational light curves of trans-Neptunian objects, large ones, with the speed survey. Cool. So at 3.6 and 4.5. So we're going through that now, and I think we have some copies.
Oh, cool. Nice.
Benicia, I also do asteroid spectroscopy.
Great, and I met you at a conference, right?
Yes.
I think so, yeah. Thanks, and what are you working on?
Oh, my name's Christian. I'm an undergrad here at UCF, and I'm doing aerospace engineering.
Okay, great. Thanks for running the show today.
Thank you.
And you said there were a few people online.
Yeah, so there are about like 4 or 5 that are online currently.
I see Dan is one of them. So.
Yeah, so.
Great. I don't know if anyone online wants to say hi real quick, but you're welcome to, if you would like to.
Hi, I'm Wesley Chambers. I work with Phil Metzger and Dan Britt. I'm a grad student working in Plume soil interaction.
On what?
Plume rocket. Plume,
oh, okay. Okay.
Great surface interaction.
Got it. Thanks. You got cut out, but now I got it.
Hello, this is Charles Shambo. And I focus on objects in the Centaur to Jupiter family transition, primarily focused on observations of the Centaur 29P. And also I have an observing campaign looking at Jupiter family comets that have perihelion larger than 4.5 AU to see if there are any like trends between like the transition from Centaur to a Jupiter family comet.
Okay, thanks.
Hey, this is Stephanie Jarmak. I'm a graduate student working in the Center for Microgravity Research.
studying early planet formation and small airless bodies.
Thanks.
I'm Dave Goldstein, UT Austin. We've done some work on the Pluto-Charon gas exchange problem and also on the rocket plume regolith interaction problem.
Howdy, great. Okay, well, thanks everyone. So I will kind of pick and choose what I'm going to talk about just because some people in this audience already have a fair amount of expertise and some people are probably still picking up some of the Pluto-Charon system basics. But again, keep in mind what you're interested in hearing more about because I can tailor it to that. So really quick overview of New Horizons. Let me move this out of the way. We launched in January of 2006. I always like to say, like, I don't know what you were doing in January of 2006, but I was a senior in undergrad and someone on the mission, Fran Bagenal, was a professor of mine. And so I got to hear about the launch. And I specifically remember her talking about how the alignment of the planets really affected her life because there were several launch windows for New Horizons. And if we had gotten a later launch window, we would have been several years later getting to Pluto just because of Jupiter would have moved a little bit and we used Jupiter as a gravity assist. And Pluto would have moved a little bit by then too. So that was fun. I got to learn about New Horizons as an undergrad. And then New Horizons, this is also a good trivia question, was the fastest launch off of Earth. It is not the fastest spacecraft at the moment because Voyager is still beating us. Voyager got several more gravity assists. We only did one at Jupiter. But we got to Jupiter in just a little bit over a year, which is pretty darn fast. And then we took 9.5 more years to get to Pluto. And we had our big encounter in July of 2015, which is starting to be a while ago now, 4 years plus. And then we were lucky enough to find another smaller object even farther out called 2014 MU69. It has a nickname of Ultima Thule, and it will be getting an official name in about a month. So I can't say what it is yet, but the world will find out the official name of this object that doesn't sound like a license plate. I think it's in the middle of November that it'll be announced. And so we were lucky enough to find this object. We actually didn't find it until 2014, hence the name. And this is another fun space trivia fact. This is the fastest object from discovery to basically exploration with a close flyby of any object in the solar system. And so I'll talk more about these guys. We used to have this bumper sticker for the 9.5 years plus getting it to Pluto. But now we get to have another bumper sticker. And I just realized we haven't made any fun bumper stickers for 2014 MU69, so we should really do that.
Small bodies have rights.
Definitely. And I just will do a shout out to a lot of different organizations and places and people, let me get off of there, that contributed to the success of New Horizons. And this is just even a sampling of those. There are so many things that had to come together for us to be able to do what we did. In particular, kind of a fun thing is all the occultations that we went to, and I can talk more about that. I have, if you would like, I have slides. We would not have been able to target 2014 MU69 as well as we did, and we may not have gotten our high resolution observations if we didn't have help from all of these places and a lot of locals helping us get the data we needed. And so this is a great, interesting technique for learning about small bodies, even in the very distant outer solar system. So Pluto was at 33 AU when we got to it, and MU69, maybe it was 32. Anyways, something around there, and MU69 is at 43 AU. So we were able to get information about the shape of this body at 43 AU, and it's only 35 kilometers across, by using this occultation technique. So yeah, lots of things, lots of places, lots of international collaboration. And so it's nice to see that all come together. Okay, I have changed the slide, but it hasn't gone yet. Okay, great. So I'm just gonna do a few very quick basics about Pluto and Charon, which I think most of you will be familiar with. Is a size comparison with Earth. Pluto is about 1/6 or so the size of Earth, and Charon is about half the size of Pluto. And so Pluto's not too far, it's a little smaller than Earth's moon. And the interior of both bodies is about 2/3 rocky materials and 1/3 icy materials. And so the majority of the icy materials is our standard water ice that we are familiar with. Neither Pluto nor Charon is big enough to have any higher phases of ice in it. It's all ice 1. And then there's some other fun ices that we call exotic ices on the surface of Pluto. And these are some of our early maps of the composition of these different ices. We have carbon monoxide, nitrogen ice, and methane ice. And you can see their distribution across Pluto here. And there's this fun bright spot in both albedo and kind of a composition hotspot, if you will, that turned out to be this very large nitrogen ice sheet, which I will show you more of. But these are the basics about these bodies. So when you're looking at the surfaces, you kind of have some idea of what is there, because these create interesting and unique features on Pluto. Okay, so I just want to pause for a sec and ask real quick what people, if you have something in mind that you really want to know more about, and I will let you know if I have stuff prepared on that. And I also have just things prepared to talk about, but I just want to make sure I get to the things that people really want to hear more about.
Hi, Kelsi, this is Julie.
Hey, Julie.
So I'd love to hear about what you think of the population of small bodies in the Kuiper belt based on the impact cratering. And if it's different than you thought, if it's different than in the inner solar system.
Yeah, great. Thanks for asking. I'm happy to talk about that.
I'd like to know about what you don't know about Pluto.
Oh, yeah, okay.
Still that you have been observing and discovering what you still struggle about.
Yeah. That's actually a great question, and just if you didn't hear what Emily said, she was saying she'd like to know what we didn't hear about, or what we haven't figured out completely yet about Pluto and Charon. Fortunately, or unfortunately, however you want to put it, there's tons of those things. So that's a good thing. I'm happy to talk about that too. I should say my background is a little bit more on the geophysics and geology side, but happy to try to speak to that composition as well.
To follow up on that question, you should list the sort of top 5 topics that somebody who is looking for a PhD topic should think about.
Yeah, I'm not sure if I'll come up with 5 off the top of my head, but I'm also happy to follow up on that question.
2 or 3, because people always come to me and say, everything's been done.
Yeah.
And I say, almost nothing has been done. So, well, what hasn't been done? I don't know what hasn't been done.
No, I remember feeling that way, but I also definitely on the side of nothing's been done at this point. Yeah, no, that's great. I'll keep that in mind. Those are all really good things, but I'm also, if someone has something else, happy to hear that. Okay, well, I'll touch on those, and if you think of more. So I thought I would start with a little geology tour of Pluto, and this will answer, let's speak to at least some of the what are the unknowns topic. Let me switch applications here. It'll probably take a second. There we go. Right, so let me zoom out just a little bit, although this is kind of a big file, so it starts to think when I zoom out too much. This is a global view of Pluto in a simple cylindrical projection. And so that just means, for those of you who are not familiar, you take the globe and you stretch it out. And you'll notice right away that there's some places we have much better imaging of, and there's some places we have very blobby, patchy imaging of, and that is because of the nature of the flyby. We flew by Pluto at 30,000 miles an hour, or 14 kilometers per second, And so we saw one side of Pluto really well, and the other side we only saw as it was rotating into our view on approach, and a little bit on departure as well. So if someone just wants to pick a feature that you'd like to see closer, that it's a good way to start. Anyone? Yeah.
So there's some really tall mountains on the left edge.
Yeah. Let me zoom in here. I'm gonna turn on a different thing. Let's go to this one. Yeah, so this is Sputnik Planitia, as I believe it is officially known now. Yes, this one's official. This very large nitrogen ice sheet that makes up the left side of Pluto's kind of bright heart feature. And as Phil was mentioning, along the western edge here, there's a whole bunch of these kind of broken up blocks. We call them mountains, and that's a perfectly fine name for them, but they actually resemble chaotic terrain, as we call it, quote unquote, that's the official term, on other icy worlds like Europa. And even on Mars, there's actually this kind of broken up looking terrain, although it probably has a different formation mechanism. I actually have a student working on these mountains. And we're going to submit a paper to our special issue that we have for New Horizons results. And I was just working on that last night for her. But yeah, so we think these are bits of the crust off to the side of this big nitrogen ice sheet. So the original formation for this basin that is filled with nitrogen ice, we think was a very large impact that happened early in Pluto's history. And there is kind of a swell of the topography around the edge of this that could basically be showing us some effect of, let me see, this is an older DEM, but you might still be able to see it. Some of the effect of the ejecta of this very large basin. But other than that, we don't have a lot of signs left from this original very ancient impact. So we think that this basically created a cold trap. Pluto's atmosphere only gets colder as you go closer to the surface. It doesn't have really much inversion or anything like that. So if you're going to deposit nitrogen ice in the coldest place, that'll be at the bottom of some kind of topography. And so we think that this probably been filled with nitrogen ice for a lot of Pluto's history, and that it grows and recedes with Pluto's seasons, because Pluto has funky seasons because of its tilt and its axial tilt and its orbital tilt. So then in addition to all this, which is mostly nitrogen ice, but also has carbon monoxide, most likely in solid solution. And then there is a strong signature of methane here, but we don't know how much of it is a surface coating and how much of it is mixed into the ice. So in these guys, though, we think all these blocks, here I can point with the mouse, all these blocks along the edge are bits of water ice crust. And there could also be some kind of methane in them. And we say that because, I don't know if I can find that real quick, but we see some layering in some of the walls of the blocks. Let's see if I can show you one real quick. You can't see it super well here, but there's a couple of examples here. And we see this layering in other places on Pluto. We see it in some of the fault walls, and we see it in some crater walls. And so we think that there may have been some episodes of deposition in Pluto's past, but mostly these are probably made out of water ice. And the fun fact is that water ice, pure water ice and pure nitrogen ice at Pluto's surface temperatures, which are about 40 Kelvin on average, have the same density contrast of about 10% as water ice and water. So these blocks could actually float in the nitrogen ice. And some of these are really big right now, and we don't think they're probably floating at the moment because you'd have to have a giant root, and it's just not deep enough along the edge of the basin to support that. But some of the smaller ones we definitely do think are floating, and I can show you some examples of that. Oops, come back. Like these little guys that kind of come at the intersection of this polygonal terrain. but these larger ones we think are probably grounded. But still, just having a little bit of buoyancy could have helped with the destabilization of these blocks. We don't know if they've really moved very far from their current location, but they could have moved, been translated a little bit. Does that answer your questions about blocks? Yeah.
There we can see this patchy, kind of flat region. The difference in color between the bottom right corner and the other part that is kind of darker, does it have any correlation with composition?
Good question. So not in what we can see. There's kind of a problem on Pluto where everything gets kind of covered with a thin coating of methane. And anywhere that's not dark, basically. Let me show you that map real quick again. So basically anywhere that's not dark, that's bright enough to have methane, bright enough and cold enough to have methane deposit on it, basically gets a big coating of methane. And it's probably seasonal, so it changes probably a little bit, but that kind of unfortunately blocks some of the signals that methane covers over. So it's a good question. And you can see here, there might be a little less CO. There's this is kind of the dark, let me use my mouse. This is kind of the dark northern part here, but it's a pretty kind of patchy, not super strong signal. And this was some of Will Grundy's earlier work, and it's a good question. I don't know if he's kind of returned to try to suss out any more differences there.
Is there a difference in the visible color?
Not that I know of. It's a good question. We could check though. I don't think I have the color map here. But it is definitely darker. And
I'm wondering if it has less CO and less nitrogen and more methane, maybe it has also a little bit more organic. So
I think, right, yeah, no, I think we kind of assume it has a little more organics, something maybe kind of tholin-y like the rest of this dark material. But I'm not sure if it's actually been seen in the composition signature or not. And probably someone has looked at that. So we could try to find out. Yeah, Phil?
Okay, just west of the blocky material.
Over here?
Yeah, you're right. Just up a little bit. Move your cursor up a little bit. Down a little bit. To the right a little bit.
This thing?
Could you describe that?
Yes, I'd be happy to describe that. Let me turn on the high resolution and zoom in here. There's also like a slight delay. So like if you say down, and it takes like a few seconds for the mouse to move. So let me zoom in here. I thought this hit that, it doesn't. Okay, let me try another different one. These are not perfectly lined up because they're an older data set, but it was just what I had easy to display here. Okay, so this is one of our second highest resolution strip that shows this little guy here. And it definitely looks better on my screen, but in any case, I think you can still barely see that there's almost some linear features in here. And I'm happy to show it to you on my screen too at some point. Personally, I think this is a remnant glacier. It's just a little patch of nitrogen ice that's in this low area here that's left over from previous larger glaciation events. So right now, the way the seasons are going is that the northern part of Sputnik Planitia is sublimating and stuff is redepositing in the southern part. That's the way the seasons are going right now. And so more and more of the northern part of Sputnik Planitia is probably losing mass. So I personally think this is a remnant glacier. Some people think it's a frozen lake, but I think the morphology is more consistent with a remnant glacier.
So the wider boundary, is that an ancient remnant of its outline before it contracted?
Yeah, and people have definitely thought about that and speculated about that. I'm actually not sure it's really that strong of a boundary because there's all sorts of, kind of crumbly stuff even over here to the southern part of it. Oops, sorry.
But
so
what's interesting is just by glancing at it, is that like all one altitude, that outline?
We don't have, well, Paul Schenk might have, but the rest of us don't yet have the topography for this high resolution strip. It's not that easy to do. you won't get this high of resolution on the topography itself because it has to be combined with a lower resolution image. So I'm not sure if we'll be able to say that, but it's a very good test of that idea. But I guess more for me is there's glaciers everywhere. And to have one spot somehow be liquid at the surface for an extended period of time is pretty difficult. I will show you a couple more glaciers because those are fun. Yeah, so if you're not already familiar, there's this interesting polygonal pattern here, and that's thought to be formed from convection of the nitrogen ice. So this is like bulk wholesale flow of the material in these convective cells. And just the heat flow from the interior of Pluto is enough to do that because nitrogen ice acts kind of like water ice on Earth, because water ice on Earth is always very close to its melting temperature. I mean, we think of it as cold, but it's really not very cold. It's not very cold on Earth. As I mentioned, the surface temperatures on Pluto are around 40 Kelvin on average. And it depends, where you are, if you're in a dark or a bright spot and what the season is. But nitrogen ice's melting temperature with like a little bit of atmospheric pressure is about 63 Kelvin. So it's always very close to, quote unquote, its melting temperature on Pluto. And that's very similar to ice on Earth.
So did you just say that the polygonal regions are convection cells?
Yes, that's the leading hypothesis for those. And how deep is the convection? That's a good question. So there's been a lot of modeling on this because it's actually, interestingly, something we can model, although we do need a lot more information about nitrogen ice. Just saying. There's not that many studies on the rheology, and they're kind of conflicting. But basically, the interior heat from Pluto, even though it's not very much, it's about 3 to 5 milliwatts per meter squared, and an average value on Earth is more like 100. Even though it's not very much, it's still enough in all the models that have been done to drive convection. Now, the problem is you actually could get too warm at the base. And so you might get melting instead of solid state convection going on. And so there's been some discussion of like, what is the deepest thing you'd have before you build up too much heat at the bottom and you're just gonna melt and not, really get the convection going. Which most people say is like a couple of kilometers. And this basin itself originally was probably like 10 kilometers in the center as the deepest part. That's what you could get if you take something equivalent from somewhere else in the solar system. So it's somewhere between a few and 10 kilometers, although it's probably not as deep as 10 kilometers today. And it doesn't fill the entire basin either. So it's about a couple of kilometers lower than the rim of this feature today.
Could you zoom out the pits and talk
about
those?
Certainly. Let me also check the time. Okay, and I will show this one glacier while I'm getting to the pits. So this feature here is basically flowing. All this brighter kind of smooth stuff is ponded nitrogen ice. You can see it ponds in all the lows up here for the most part. And then it's flowing back into Sputnik Planitia. And this resembles very much glaciers that we see on Earth. So there's a few familiar features on Pluto, but then there's a lot of ones that we don't know what's going on. So then there's a wide range of pits, and let me turn on a higher resolution thing. Sometimes they almost look like organisms or something, but they're all thought to be probably from sublimation of the nitrogen ice. And you could also get some elongation of these from kind of bulk flow of the nitrogen ice. There's various theories about how to get them to look kind of elongated, but you can see there's also some circular ones. But we think it's from sublimation. What initiates it in a given spot is not entirely clear. But we think they're all from sublimation of the nitrogen ice.
The nitrogen that is sublimated there, how far would it go? Is there any model of the transport of volatiles?
So Sylvia Protopapa has done a little bit of this, not necessarily on this scale, I would say. We should check her papers. Of course, people like Leslie Young and Kathy have done more global But I don't know if anyone's done something quite on this scale. Yeah, like where does it go? Right, if there's not, yeah. It's possible that we can't see them, but there's not like a lot of rim. Like, you know, we don't see like a rim, but it might be very thin, or, you know, if it gets spread out. There's also some that are like less deep, and it's not clear if they're coming or going, the pits. Like you can see here, there's some like shallower ones. So yeah, that's definitely one thing that we don't know everything about yet.
I would have thought the key thing to try to explain is the linear features and the fact that the spacing between lines is so consistent. And by analogy to Earth, I would have thought that a good analogy is cloud formation, which is also a phase change. Like
yeah.
sublimation. It's a phase change, which is not common. But they form linear features, little puffs that are in lines because of the convection rule. So I would have thought there was an evidence of convection going on. You know, heat transport, leading sublimation, also can lead to convection.
Yeah, so, I had not thought about it obviously in relation to clouds, so that's an interesting thought. This is a region where we don't necessarily think convection is going on. It doesn't have the cell pattern. Yeah, it couldn't be. Yeah, I don't think anyone's thought about whether there's convection occurring at this scale. Let's see, for example.
How else you could explain the amazing consistency all over the ice sheet?
Yeah, there is some differences, and actually,
the geology of ice might provide that length scale.
Yeah. So this, for example, this little darker feature, this big patch is about 11 kilometers across. So that gives you some idea of the scale. There is someone who's kind of going through and trying to do more quantitative comparison of the characteristics of these pits across the ice sheet, but they actually do change as you move up and down. So that could be another clue. You can see some of these, interestingly, seem like they're exposing the surface below the nitrogen ice. This kind of dark crumbly stuff looks very similar to some of the terrain to the outside of the ice sheet. So it's not really clear why some of them expose dark material and some of them don't, even if they're close to each other, because it's not really thought that there should be really big differences between the thickness of the nitrogen ice in different areas, because it will kind of flow and even itself out. So this is definitely still an open question. Uh-oh, did it disconnect?
Quick thing, if you guys would like to ask a question, please just press the tail mic, whenever you want to speak, just so people online can hear you.
Yes, if we forget to do that, repeat it.
Yeah, if you could, yeah.
Yeah, just remind me if I forget to. I'd be happy to repeat the question. I think it seems like I lost the Zoom. Maybe I lost the internet.
Let me check.
It says no internet access. Well, now it says connected. Sorry, people online. Because it says, Zoom says it's connecting. Okay. Maybe I should try the link again.
Yeah, just try the link again.
Okay.
You should be, the UCF Wi-Fi acts up sometimes, so it's not really that fun.
It's
your image. We see a picture of you on the screen. We don't see your computer.
Yeah, I can see it on this other screen here. Let me try getting back online really quick here. See if that makes it happy. Okay, now that's happy. So let me rejoin the Zoom.
We can't see your presentation, but we can see you and hear you.
Yeah, I think I'm getting back on Zoom, so hopefully that'll fix it. All right, no video. Okay, well, I'll show a few other fun things on Pluto, but Pluto can definitely steal the show. So we'll get to a few other topics if people are interested here before the end. Maybe. There it goes.
Okay, there we go. Let me just double check.
Yeah, the internet's kind of going in and out, but hopefully it'll stay.
So you're back on, so you should be able to screen share and it should be good to go again.
Okay, let me try this again.
There we go.
All right, so moving away from pits for a moment, just so I can get to some other fun features. And also Julie's request. This is a feature that I'm currently working on. It's called Right Mons. informally or formally, I don't remember. And it's a very strange feature because it's got, you can see this hummocky surface. It's this mound, the kind of central mound, wait, let me use my mouse. The central mound here is about 4 kilometers high with respect to the surrounding terrain. And it's got this enormous central depression, which I try not to call a caldera because it's actually very dissimilar in morphology from any calderas on Earth. It goes to the base of it basically goes down 4 kilometers. So, and it takes up about 1/3 of the entire shape of the feature. So you can imagine if you take a triangle where the long side is at the bottom, and you rotate it around one of the points that's at the bottom, that's what the shape of this thing looks like. It doesn't look like a mound with a hole in the middle. It's very strange. We have topography for this area. So yes, yes. So I have some other slides on this. I don't remember if I put them in this presentation, but you can stretch the image and you can see in the dark area here. And that's actually in part because of one of our cameras that's has very good dynamic range, basically. And thank goodness for that camera. Let's put it that way. Because also the dark parts on Pluto were hard to see with one of our cameras. And so another camera that had basically a large dynamic range, it's a scanning camera, and that could get basically good signal to noise, was essential for seeing in those dark areas, both shadows and the dark material. It's the MBIC camera. All right, so anyways, I don't have time to talk about all the amazing things about this feature, but it's got a lot of cool aspects, including this very strange shape and very strange textures on the surface. And if you will notice, there's very few possible impact craters. So this was weird because it looks young, but it's not made out of nitrogen ice. And we know that because nitrogen ice cannot maintain topography. It becomes flat, like you see in Sputnik Planitia. And so it wasn't known how you could mobilize, and it's still not known, I should say, how you can mobilize something like water ice at the surface of Pluto. And it could be water ice mixed with other things. But again, we have very little rheology data on that. So that's always a vote for more lab rheology work. Anyways, I'm working on a paper on this topic, and it's a very cool feature. So the kind of big takeaway unknown is how to possibly either retain heat in the interior of Pluto that you could use to do geology in the more recent times, or how you could create new energy in Pluto. And there's really no great option for that. There's no tidal energy in the system. So some ideas that people are exploring is how you could potentially have retained heat in Pluto over time. So yeah, so there's a lot of open questions about the interior and how to produce these features and that kind of thing. For composition, unfortunately, this feature is mostly covered in methane ice. Oh, darn methane ice. So you can't see much past that. Some of these there's a few like darker areas, and those don't have as much methane, but they just look kind of the same as Cthulhu in terms of tholin-y type material. So we can't really get at the composition of the bulk of the material in this feature from our spectral data.
Are you seeing any compressional features in this thing?
Well, I have one idea that all of the lumpy stuff is actually a kind of a compressional folding type giant Pahoehoe thing. So the whole feature is 150 kilometers across, and these little smaller lumps are like 8 to 10 kilometers across. So it's a huge scale, so I'm not saying for sure that's the right idea. But it's hard to kind of get a consistent lumpy shape if it's not all made from a similar process. And it also kind of resembles some terrain on Enceladus. In the South Pole, in between the tiger stripes, they have kind of also kind of a lumpy thing, and that some ideas about that is it's from compression of the material, kind of like, folding a rug, pushing a rug, whatever that's called. Yeah. But otherwise, global scale compression, not really.
So Pahoehoe would be lower viscosity because it's hot and it's flowing downhill, lumping up like that? What are the driving forces and that would cause this?
That's a great question, and that's why it's just kind of a hypothesis at the moment for how to get kind of a consistent size of these lumps. It would have to be, we don't even know for sure if the material is coming from the center of this feature. We just kind of suppose that it might be for some of our, trying to model this because it's kind of concentric around that depression. If you look in the interior, you don't see any obvious signs of plumbing, for example. So this feature is probably very different than what we're used to. So you kind of have to keep that in mind. And the fact that the area around this mound looks like it might be the youngest. So you can see over here, there's some kind of terrain that's similarly lumpy, but it's more fractured and broken up. So we've been speculating that maybe this is an older version of this terrain. Anyways, we have some clues, but they're not, it's very different from a traditional volcanic setting where you kind of know where the material is coming from and where it's going to. We don't have a lot of directionality for any of this stuff, like, flow indicators or anything like that. So it's just a weird thing. Yeah.
In icy bodies, we typically invoke cryovolcanism and salty material with nitrogen mixed in water to explain what we think would be the volcanoes in icy places.
Yeah.
So, but this is why you go there are so many. There are not many detections or observations.
Yeah. So I definitely work on this. And at one point, I made up a bunch of slides for a presentation that was like, for any feature that someone could potentially ask me about, because people often say like, oh, is it like this thing on Titan? I'm like, no, it's not like the thing on Titan. So this is really unique. And it's really different than any other of the potential cryovolcanic features anywhere else, except maybe at the South Pole of Enceladus. This is the only one that has some similarities, but it's hard to tell if it's really similar. Yeah.
Does the existence of a regional feature like this suggest anything going on in the mantle, like a hot spot?
So that's a perfectly good question, and we've tried to consider why it might be in this location, but also keep in mind there is another feature that we think is somewhat similar to the south, but we weren't able to view it as well, and it's even bigger than this feature, and we don't know how far this terrain extends. Basically, I don't think I have the one that shows the, there's another one like right over here, but we didn't see it as well. So we don't actually know how far this terrain extends. So it's a little hard to know if the location of this feature is meaningful or not. So yeah, like some people have tried to relate it to the basin. Could there be some structural thing related to the basin that created a weakness that allowed material to come up here? But they're not really like, the next one farther down, they're not like concentric around the basin or something like that. So it's still an open question as to whether the location is meaningful and if it implies anything special about the interior at that place.
Rick Ward has a question online.
Okay, great.
Just right there.
Oh, you want me to ask it? Okay.
I'm reading it, but you can ask it too.
You do both.
Is water?
Yes. Go ahead and read it.
Go ahead, Christian. Go ahead and read it.
Okay.
Yeah.
With the different boiling/freezing points of these chemicals, how differentiated are these features? Is a water boulder pure water or mostly water?
Yeah. Are you asking like what else could be mixed in here, or?
Well, I know that they all have some bits of other stuff, but for instance, would there be a lot or a little of ammonia or methane or even nitrogen or other things like that?
It's a good question. I probably don't have a great answer. We have some constraints just based on the topography. So if something maintains its height, we know it's not mostly nitrogenized.
Right.
And we have some constraints based on what we think is there, like you were kind of alluding to here with differentiation. But there's a lot of room in the models for different stuff to be left over at this point in Pluto's history.
Right. So, for instance, if you see a smooth, flat plane, that's an assumption that it's probably mostly nitrogen. Is that probably a pure blanket of nitrogen? Like if you scooped up some of it in your hand, you would have nothing but nitrogen in a frozen hand?
Yeah,
or
that's a
is
good
there
question.
other stuff probably mixed in with the nitrogen, for instance?
So in some areas, we do know that there's carbon monoxide mixed in with the nitrogen, just from the spectral signature and the way the spectral signature matches laboratory data where those two things are mixed together.
Mm-hmm.
So there's probably very few areas of completely pure anything, but there's probably some places that are closer than others.
Okay, thank you.
Yeah.
That's basically my question.
Yeah.
Based on this image that you are showing now, I can see that you can kind of see that the taking away the Sputnik planitia, the region where nitrogen deposits and the region where CH4 methane deposits is kind of complementary.
Yeah, I agree.
And you would expect that nitrogen deposits on the coldest regions and methane in the ones that are a little bit warmer.
Yeah.
So why is the coldest region on Pluto not on the poles?
Oh, good question. Well, partly it's because of the bright albedo, because it's so bright. It's really high albedo, but also because of the seasonal cycles.
It's because of the orbit?
Yes, and I unfortunately am not the expert on that topic. And they're very confusing, so I can never keep them straight. But there are times in Pluto's history where the poles receive more insolation. And I don't remember which time we're in. Pluto has several million year, basically similar to Milankovitch cycles. There's different time scales, like 2 to 5 million years is one time scale. And then also the orientation, the actual orientation of the pole changes. So like whether it's the pole is pointing towards the sun at perihelion, and sometimes it's not. So there's a lot of different time scales that affect the seasons. And it's something we can check on, but yeah. So it's a combination of it being really bright and also the weird seasons. And it's low too. So the atmospheric temperature is decreasing. There's things are stacked up in favor of Sputnik planitia being a cold spot. Okay, so I know we're getting low on time.
Sorry,
yes,
I have a question. Why in the nitrogen there is these lines? Like you can see there.
Yeah, this is an
specific
artifact
lines.
of the observation,
Wow.
which was it's a scanning instrument. And this is the direction that it scanned. So yeah. So
I
that's
thought
an
maybe there
artifact.
was some.
It's a good question though. Yeah, it's some weird seasonal thing or something. But okay, since we're getting short of time, I just want to quickly mention another kind of big result, and then I'll end with just a couple pictures of ME69. So Julie inquired about this very kindly. But one thing that we plan to do, and when you're planning a mission, you're like, we're going to do all these cool things. And then sometimes you actually do some of the cool things. So that's fun. But one thing we did want to look at is the broader population of the Kuiper belt in terms of its sizes, how many big, how many small objects, by looking at impact craters on could have been either Pluto or Charon. We didn't actually know if Pluto would have any impact craters. We thought maybe they had all been erased. Turns out Pluto did have some, which is useful. But Charon is actually a better place to look at impact craters. And it's also a very cool place. Unfortunately, Pluto always steals the show. But just briefly, some fun features on Charon. The southern hemisphere is very different than the northern hemisphere, as you can see. But we think they're both pretty ancient. And that's because there's still quite a few impact craters on this southern plain. So speaking of cyrovolcanism, we think this southern plain was completely resurfaced at some point, and that created this smooth-ish terrain. And we think that happened early in Charon's history, and if someone's interested, I can go into the details later. But there's also fun ropey-looking things on Charon. We think these are probably part of the original texture of resurfacing this plain with a very large cryogenic volcanic event. because you can see the craters overprint everything else. There's very, very few examples of, this is not one of them, of where some other type of geologic feature, either tectonic or potentially volcanic, interrupts a crater. The craters pretty much overprint everything. So that makes this a great surface. This is a mountain in a moat, as we call it. And this is what, just a little closer view of this very large tectonic fracture belt that runs across Charon. And the northern terrain also has a lot of fractures. You just can't see them very well in this image.
What is the material?
It's all mostly water ice. Yeah, and there is a very slight signature of a few other things on the surface of Charon, but it's mostly water ice. We do have a few little patches of ammonia, but they're ironically not in Vulcan Planitia. They're from fresher impact craters in the north that expose some ammonia, which is interesting in another story. Yeah. Yeah, go ahead. Microphone.
From this view, those two bright craters that you can see up close to the edge, are those really brighter craters with different material?
So Charon has this interesting thing, especially in the northern terrains, where the ejecta is dark in the interior and then brighter outside, which indicates layering in the subsurface. And there's a bunch of craters that have this dark inner and bright outer ejecta. By a bunch, I mean like a handful, because there's just not that many. It's a small surface area. This actually, I believe, is lighting on the wall of a crater. And we're looking at it at a very oblique angle. And this one is actually bright ejecta. So there's definitely some different materials being exposed from the craters up there. There's a bunch of fun albedo patterns to the craters. So that's a good observation. Okay, so let me just switch to another slide real quick. So even though Charon has lots of cool geology, the craters pretty much overprint everything, so we think it's older. And we could use these craters to think about the size distribution of Kuiper belt objects, which was some of the work that I did. And the kind of the short version of what we found is that the Kuiper belt at smaller sizes, so these are objects that are smaller than about 1 to 2 kilometers in diameter, which we cannot easily see with telescopes. It looks like there's fewer of them than we might expect. And our expectations are based on the asteroid belt. And we have more observations of the asteroid belt. We've done more modeling of the asteroid belt. We really thought we had the asteroid belt figured out, and we might. But this basically, I could show you this plot. I'm not going to spend a ton of time explaining it, but this is a model that fits very well our observations of the asteroid belt by Bill Bakke. And this is just showing the size of the crater along the x-axis. And this is a relative number, which I won't go into a lot of details about, but it's related to how many there are. And this is what we find on Charon. And so you can see for craters smaller than about 13 kilometers, which is for objects that hit Charon, smaller than about 1 to 2 kilometers, there's a very different shape. And by the time we get down to the smallest ones we can see, we don't really know what's happening after this. There's at least an order of magnitude difference between the number of objects we would expect in these populations and how many there are based on collisional evolution, which matches the asteroid belt very well. So there's a lot fewer small objects than we might have expected to find based on what we know about small body populations like the asteroid belt. And so we're still exploring what this means. It means either you didn't make them or you made them and you got rid of them. And there's a few ideas of how to maybe preferentially get rid of small objects, but that's harder to do than just not making them in the first place. And so this is kind of an interesting constraint to have another example of a small body population and to think about whether you can do this from the same processes that we use to model the asteroid belt. So whether collisions occur differently for some reason, whether it's just not collisionally evolved and the asteroid belt is, these are still open questions. Yeah.
Could I ask a question, Kelsi?
Yes.
So did you look into the idea that maybe these smaller craters are just being I don't know, damped by the fact that it's water ice, like that the surface would basically not show these smaller craters for some reason?
Yeah, that's a very good question. Let me go back to the picture of Charon real quick. And yeah, so we do still see them. And the velocities, the impact velocities are about, oops, let me go to a different picture. The impact velocities average on Charon and Pluto both are about 2 kilometers per second. So they're not crazy low impact velocities. There we go. They're not crazy low impact velocities, and we do see small craters. So it's possible there is kind of a distribution to the velocities that impact Pluto and Charon, and there is kind of a tail in the low velocity, but it shouldn't get rid of most of them, for example. Like it's not going to get rid of an order of magnitude. So to give you some numbers real quick, in the smallest size bin, there's about 30 craters, and we would need 300 in order to match the asteroid belt. So yeah, so it's a very good question, but we don't think that that's getting rid of 9/10 of the craters.
I see. And so there's no reason to believe also that these 30 craters that we see are just younger, like leftovers, and maybe in another geological time scale, they will be gone?
Yeah, that's a good question too. So we don't see any intermediate states of erosion. So like we don't see craters that are half filled or half erased or 3/4 erased or 1/4 erased. So that's the thing that's kind of, yeah, that makes us think that there's mostly only been cratering going on here. First of all, Charon never had an atmosphere, most likely, maybe very, very early on, but probably never had an atmosphere. And we don't really see any intermediate states of the craters being erased. So it's hard to think of a geologic, yeah, that would happen only at certain times or only somehow completely erase some size of craters and then leave the rest. You know what I mean?
Yeah, it makes sense. Thanks.
Yeah.
In the inner solar system, the crater saturation age is like 4 billion years. This looks like it's way short of crater saturation.
Yes.
So it does kind of look like the crater saturation age would be more like 40 billion years here.
Probably, yeah. So I've been meaning to do a direct comparison of the impact rates. So I could say like, you know, Charon has 1/2 of the moon or something, but I just haven't gotten around to doing that. It wouldn't be that hard to do. But the impact rates are lower here. So there are estimates, and the estimates say that this is older than 4 billion years based on the number of craters here. Of course, there's some wiggle room in the estimates because we don't know everything, and there's error bars on that too. But by all accounts, this is an old surface.
Yeah, and if looking at the elevated terrain versus the lower terrain, or the northern versus the southern, or whatever you want to call it, it doesn't look that much different.
Yeah, no, that's right. So the overall densities, the number of craters on the north and the south per area are pretty similar for the size range that overlaps that we can see. So they're both predicted to be pretty old. Statistically, you can't even really tell that the southern plane is younger. They're statistically within error bars of each other, but we don't have a lot of overlap in the data. And we pretty much know this is younger because it unlaps the northern terrain, but not by a lot, probably.
If I may again, it's me again.
Well, you had to wait this whole time for your topic, so I think you should.
Yes, these are impacts in a very different material than what we would expect, like on the moon or on asteroids, right? Because it's all icy material. So are you using the same scaling laws that tell you how big the impactor was and how fast it was going than for asteroid surfaces, for example? Or are you using different laws that do account for this fact that this is ice?
Yeah. Good question. So remember, ice is a mineral too. I feel like I would be fun to have a t-shirt that says that, but you know that. So I'm used to working in the outer solar system. So to me, ice is just, or rock is just the ice of the inner solar system. But basically they do take it into account. I use the Hazen and Holtz-Apfel scaling laws, and In the gravity regime, which all of these impacts that we can see are in, they're all big enough that we can't see the ones that are in the strength regime. The gravity regime, it basically only takes into account density and porosity, because strength, quote unquote, doesn't matter in that regime, for the initial formation at least. We do see some differences because ice has a lower strength. So we do see some differences in kind of the final morphologies based on collapse of like terraces on the walls. This again looks better on my screen, but you can see some little warbly stuff here. And this is very typical of impacts. And there's another one up here. This is very typical of impacts into ice. We see this on icy satellites as well. And it's thought to be kind of a folding warping of the floor. So yeah, there are some differences, but mostly kind of in the final outcome of the shape and the appearance and what other stuff is going on inside the crater. And for example, they're usually often shallower icy craters for the same size. So this stuff is kind of known and kind of taken into account, but there's certainly some wiggle room. And in the appendix of my science paper, I kind of use 2 end member materials, and that's where you get the range of about 1 to 2 kilometers. So that tells you kind of how much wiggle room there is.
Okay, thanks.
Yeah.
That's
Happy to
it.
talk to you more about it sometime now.
Yeah. Thank you.
When we're both in the same city. Okay. I think I should end with one picture of MU69 since we're over time, but it's a beautiful object. Let's see where to go. Okay, I'll show this animation.
It is also not approaching crater saturation.
Definitely not. So this is an animation made by a very talented amateur. You can see his name down there. I'll mispronounce it if I try to say it. It's a little slow here, but it's switching between 2 different images. And on the left is a lower phase image. When it goes all the way to the left, like now, you can see more albedo variation. And then when you get to where the head is all the way to the right, that's a higher phase image, and you can start to see more topography over on, this is the limb here, where it goes into the night side. So this is also just kind of fun example of how different things look when you have different lighting and observation geometries. So yeah, the MU69 actually kind of was a great test of the question of how many small impactors there are, because MU69 is only 35 kilometers across, so it can only have small impactors. It just so happens that this largest possible impact crater here, which is informally known as Maryland, is about where the transition diameter is that we see on Pluto and Charon. And even taking into account scaling, which we do for this object. So there's just not a lot of craters. The lighting definitely affects your ability to see it kind of on this right half. But on the left half here, I'll just go to the next picture here. This is showing those same, this might be a slightly different one. Anyway, same kind of concept here. You can see there's plenty of terrain up here where if there were craters, we would be able to see them. And they're just not there. So it's a funky object in its own right, and it also doesn't have a lot of small craters on it. And that's it. Thank you. You guys had all really good questions. This was fun.
More questions online or in the room?
I got one online. So MU69 is pretty clearly a contact binary. Perhaps these 2 things came together slowly enough, and that's what's left. You had your mountain in a moat.
Yeah.
How do you know that's not kind of the same thing? The mountain gradually, somehow, gravitationally, magically touched gently enough and just sank into the ice.
It's a very good question. I'm not sure if we could totally exclude that hypothesis. It's just a weird feature. People have speculated that other options are that it's like the edge of a block, of a tilted block of something that's still poking out and didn't get completely subsumed by this volcanism. But you know, right now we see it with this, the kind of the terrain coming, the volcanic terrain coming up to it, but not overtopping it. So it's really hard to say what the original form of it was because, you know, we can't see all the way down to what might be the base of it. I don't know. It's a good question. It could have been a very, very low velocity scrap of something, but it also could just be related to the geology of the region.
Okay, I've heard people, I think maybe Alan, talk about the potential of a subsurface ocean on Pluto that might still be liquid.
Yep.
How can you get that from the observational evidence?
Yeah, it's hard to do from what we currently have, except through modeling of geologic features and saying you need this much heat flux for that or something like that. People have tried to do that for a few different types of features. But just the fact that we have young terrains is kind of implying that there could be enough heat flux to maintain an ocean at the base of the shell. So this would be pretty far down, 100 plus kilometers, because yeah, it would be at the base of the shell. I mean, some liquid could migrate upwards through various geologic mechanisms, but it would not be a subsurface ocean like on Europa. For example, it'd be a lot deeper, most likely. But yeah, no, we basically could use a lot of other types of evidence that we didn't get from a flyby to try to really nail that down. And that's one of the main motivations for sending something back like an orbiter.
So it wasn't the overall geodetic information, it wasn't the overall shape,
yes,
there wasn't a ridge or anything like that?
This is actually a topic that I work on as well, but the overall shape is pretty spherical. As far as we can tell. And that's actually a good sign for a global ocean because it means that you didn't get frozen in some more oblique shape early on. And if you have enough heat to stay circular, become circular after tidal evolution and that kind of thing, it's not a hugely strong constraint, but it's at least not a bad sign that you had a global ocean either in the past or recent present. So there's modeling that says you can maintain an ocean. And then whether we actually can prove it or not, it'd be nice to have some other kinds of data. So we could definitely get the overall shape better than we did. But we could also send stuff to learn about the gravity of the body, things like that.
Are there other more exotic phases of ice that you didn't mention that have been positively detected?
Not on Pluto and Charon. So the larger moons of Jupiter and Saturn, actually, Titan and Ganymede and Callisto, all have the potential to have, they're large enough that their interior pressures are high enough to have higher phases of ice.
I meant like more complex, like ethylene ice or something,
okay.
or ammonia.
Yeah. So non-water ices. Yes, so there have been some thoughts about methanol, and that's, I think, maybe one of the highest ones I've seen someone say they see in a spectral signature. But we've assumed that there's a lot of other higher order, heavier hydrocarbons around, and that's what makes up the black gunk.
But you can confirm this to me, that there has been some detection of hydrated ammonia around some features that are craters, so that could mean that it has been deposited from the interior and this. But how overall has been the detection, just for one feature? Or?
Okay, so this is Christina Daliore and Dale Cruikshank, plus other people on the team's work. But Dale's the one who's very excited about this. So it's around this particular fault system called Virgil Fossa. And this, I don't have the color here, but it's a little bit different red around this area. And that was kind of what initially clued them in that maybe there's something going on here. So Christina does some very complex processing, and I know it's like ratios of something to something. So it's not exactly like the most simplest detection. But I'm not familiar with that, that kind of processing. But it's around this feature, and then you can also kind of see it in some of the other terrain around here. So they think it's a hydrated ammonia signature, but there's not like a really strong geologic feature directly associated with it other than this fracture in the dark material around it. So there's not like a mound with ammonia on it or something.
It's not like a crater with bubbles around.
No, sadly not. So it's more of a diffuse kind of detection rather than more specific. And that same kind of feature shows up in some of the other kind of mottled, dark looking areas, kind of on over here as well. It's more up here. Sorry, let me go back. In this region here, there's some sort of similar type of feature. And so it's a little, I don't know, to me it's a little bit, almost seems more geometrically associated, either with like the north-facing walls of craters. But I think that's still, again, an open question to figure out what's going on with that. We do not see that signature around Riemanns. Yeah.
More questions? Well, let's thank our speaker once more.
Thank you, everyone. I know everyone's busy, so it was fun.